Okay, so this is the second video from section 8.4, where we answer or start to answer the question, where did those thresholds for rejecting the null hypothesis come from in the previous examples? Like, why did we decide that our students were below average in math if the sample average was less than 505? Or why did we decide the factory was lying if they had 4 or more widgets out of 50 fail or be defective? Okay, all right. So why don't you pause, copy, and then press play. Okay, so definition, significance level. The significance level alpha of a hypothesis test is the largest value that we find acceptable for the probability of a type 1 error. So oftentimes it's 5, 10, or 1%, okay? So that's what we call the significance level of the test. We set up the test and we've got this threshold for rejecting the null hypothesis. What significance level does it have? How likely are we to have an incorrect conclusion, okay, of type 1 incorrect conclusion? All right, so another definition. Assume we're conducting a hypothesis test, H0 versus H alpha, and we've been told our significance level alpha. Then we can find this script R, which is the set of all values of the test statistic for which we reject the null hypothesis. This script R we call the rejection region or the critical region. So this is the critical region. We've seen it before. 505 or less was the critical region for the SAT example. 4 widgets or more was the critical region for the factory widget example, okay? So that critical region or the rejection region is going to be of prime importance. The boundary point is called the critical value. So sample average of 505 on the nose would be a critical value, and number of defective widgets of exactly 4 would be the critical value for the previous 2 examples in the last video. All right, so let's go back to that SAT example, where if you remember, nationwide, the average SAT math score was 515 with a standard deviation of 116. And let's say the school district sets 10% significance level. So the school district is okay in rejecting the null hypothesis that their students are on average about the same as the nation. So they're okay rejecting that notion 10% of the time and instead concluding that their students need more math remediation because they're below average, okay? So the school district is okay with 10% of the time overreacting, perhaps, or reacting inappropriately to what the scores are showing them, right? We're going to find the value C of the sample mean, again, 100 students sampled, with under which we should reject the null hypothesis, okay? All right, so we're setting our alpha to be 10%. And if you remember from up above, that's the probability that we're going to reject the null hypothesis that our students are about average in math, given the null hypothesis is true. Our students are about average in math, okay? And we're going to reject it when our sample mean is less than some critical threshold C, less than or equal, doesn't matter since this is normal, given that our students truly average out at 515, okay? Now, I can then subtract the mean of 515 and divide by the standard deviation on both sides of here. The left side becomes Z, just as it did in the previous video. And the right side becomes C minus the mean of 515 divided by the standard deviation of 116 over the square root of 100. Because again, we're sampling 100 student scores. So that gets me the standard normal CDF evaluated at that value, C minus 515 over 116 divided by root 100, okay? Now, over here, from the standard normal table, if 10% of the time this is going to happen, that corresponds to a z-score of negative 1.2816. So I'm going to set this value in here equal to negative 1.2816 and solve for C, and I get C to be 500.13. So that means the school district is comfortable saying, hey, we've got a math problem if their sample average is below 500.13, okay? And they're accepting that 10% of the time they'll see a sample average below 500.13 when their true student population is actually completely average with a mean of 515, okay? So 10% of the time with that threshold, they might be doing more remediation than they need to, okay? Okay, so let's look at another example. So again, pause, copy, and play. All right, and I'll be referring to something in the book, so I gotta find my book here. All right, so in this example, we've got a six-sided die, and we want to know, is it a fair die or not? So the way I'm going to decide if it's a fair die or not is I'm going to roll the die 60 times, and I'm going to record the number of times I see a one. All right, that's it. So that's what I'm going to call X, the number of ones that are occurring. And I want to set my significance level for this hypothesis test to be 5%. So I'm okay deciding the die is not fair when it actually is fair 5% of the time. I'm okay making that mistake 5% of the time. Okay. Now, my null hypothesis is that the die is fair. So the probability of a one is 1 in 6, 1/6. Okay. Now, what I'm looking for is the values of C1 and C2 that I should be focused on, for which if I see less than or equal to C1 ones or greater than or equal to C2 ones, it causes us to reject the null hypothesis because, maybe I'm seeing too few ones, or maybe I'm seeing too many ones, right? So I need to account for both possibilities in order to reject the null hypothesis. Either of those things cause me to reject the null hypothesis. All right, so we need to figure out these critical values. All right, so my null hypothesis is the die is fair. The probability of a one is 1 out of 6. The alternate hypothesis is it's not 1 out of 6. Maybe it's less than, maybe it's more than 1 out of 6. The die is rigged somehow. Okay, now under the null hypothesis, if the die is fair, I would expect to see about 10 ones in the 60 rolls, right? That's the expected value of this binomial distribution. I have set my significance level alpha to be 0.05. So by definition, that's the probability I reject H sub 0 when H sub 0 is true. I reject H sub 0 when X is quote unquote not close to 10, given that the die is fair, which means that X really is binomially distributed with 60 trials and probability of success 1/6 each time. Okay, so there's my null hypothesis. All right, now there's two ways we reject H naught, when X is too small or when X is too big. So I'm going to take this 5% and split it equally into the two smalls and the two bigs. Okay, so there's a 2.5% chance that I see X is too small. It's less than or equal to some threshold C1, given that that actually H naught is true, the die is fair. And then there's a 2.5% chance that I see too many ones. X is greater than or equal to C2, given that the die really is fair. Okay, so what the book has done and what we could easily do is for X's on the low end, table 8.2 on page 260 for both of these actually, what it's showing you is the probabilities that we're seeing 0 ones or 0 or 1 ones, since this is a CDF, or 0, 1 or 2 ones, or 0, 1, 2 or 3 ones, et cetera, et cetera, et cetera. And I'm looking to see how far along this row can I go until I hit that 2.5 threshold, okay? So in between 4 ones and 5 ones, I go from the CDF value being 0.202 to being 0.0512. So that means I think I got to stick at 4. So the probability that X is less than or equal to 4 is less than or equal to 0.025. The probability that X is less than or equal to 5 is more than 0.025. So I'm going to stick with C1 being 4. Okay. Similarly, on the other side of things, what if X is too big? Well, second row here, the probability that X is greater than 16. Strictly greater than 16, interesting. Probability X is greater than 16 is 0.0648. That's more than 0.025. Probability that X is greater than 17 is 0.0338. That's also greater than 0.025. Probability that X is greater than 18 is 0.0164. So that looks like I should stick with 18. And it looks like I made a slight mistake. Should get rid of the equal sign there. I don't know why they did that. I would just said 19, but just to stick with the book, we get to there. That must be an error in the book. Actually, I think that's an error in the book. I think the table shows that greater than or equal to. So the probability that x is greater than 18 is slightly less than 0.025. The probability that x is greater than or equal to 17 is well more than 0.025. So 18 is my threshold here. If I'm wrong and this should have been 19 versus 18, fine. This is a binomial distribution. We could use R to figure that out exactly. Okay. All right. So the upshot is, with a critical region of R of less than 4, less than or equal to 4, or greater than or equal to 18, there's a 5% chance that X could be in these values when the die really is fair. So we would reject the null hypothesis even though we shouldn't have. So that's my critical region. And it turns out the probability that X is in that critical region, the exact probability is 0.0366 from adding the two values in the table. Okay. All right, one more example. And we're just going to get away from name brand distributions here. So why don't you pause, copy, and play. All right, so in this scenario, we're going to draw a random sample of 8 random variables from a distribution whose PDF is known, but I don't exactly know theta. X is between 0 and 1, and theta is some positive number. Now, I'm testing it's a parameter hypothesis test. The null hypothesis is that theta is 2. The alternate hypothesis is that it's greater than 2. Okay. The test statistic I'm going to record. So in this example, I'm going to give you the critical region. Y is going to be the number of observations 0.88 or higher among the 8 that I sampled from the distribution. So 0.88 or higher is the critical region. Okay. Sorry, it's not the critical region. That's a threshold. I'm going to reject the null hypothesis if y is greater than or equal to 5. So y greater than or equal to 5 is the critical region. Okay. Now, where did 0.88 come from? Where did 5 come from? Don't know. You know, other ways of calculating that significance level. Okay. But given this information, we want to determine the type 1 error rate. Okay. So by definition, type 1 error rate is the probability I reject the null hypothesis that theta is 2, given that theta really is 2. Okay? I reject the null hypothesis when y is greater than or equal to 5, and the null hypothesis is that theta is 2. Okay? All right, so I'm going to pause there for a moment and say, well, my y count occurs if I have an observation that's 0.88 or higher. So what's the probability that a single observation from this distribution is 0.88 or higher under the null hypothesis, under the assumption that theta is 2, because that's what I'm operating under. All right, well, the probability that x1 is any of the x's is greater than 0.88, given theta is 2, is the integral from 0.88 to 1, since x goes from 0 to 1, so from 0.88 to 1. And under theta equals 2, there's my PDF. So I can anti-differentiate it, and I get x cubed from 0.88 to 1, and I get 0.3185. So that tells me that under the null hypothesis, theta being 2, y, the number of observations 0.88 or higher, follows a binomial distribution. 8 trials, probability of success, 0.3185. So if I want the probability of y is greater than or equal to 5 under theta equals 2, I just have to add up from 5 to 8, having 5 successes, 6 successes, 7 successes, or 8 successes under that binomial distribution, which I can hand off to R, and that gives me a 0.0736. So given a critical region of y greater than or equal to 5, we have a type 1 error rate of 7.36%. So if that's the critical region you're going to stick with, you have to accept it 7.36% of the time. You're going to reject H0 when you shouldn't have.